Welcome back. So in the previous theorem, we looked at the second derivative test to determine the local max and local mean values of a function. And so we're going to apply that in another example to begin with in this video. So let's say I have the function f of x equal to e to the x minus 5x. And we want to figure out the local extreme values of f. So as usual, we have to find the derivative first. The derivative is e to the x minus 5, which is equal to 0 when if it is so e to the x is equal to if e to the x minus 5 is equal to 0, then e to the x would be 5, and then x would be ln of 5. So this is the critical point of this function. Now if I take the second derivative of f, I get e to the x, and the second derivative evaluated at ln of 5 would be e to the ln of 5, which is 5, so which is positive. So we see that the second derivative is positive at the critical point, so that means the function is concave up at this critical point, which means f has a local minimum at ln of 5. So what is f of f evaluated at ln of 5? It'll be e to the ln of 5 minus 5 times ln of 5, which is 5 minus 5 ln of 5, and here is the graph of this function, and you can see that at the critical point ln of 5, the function value is 5 minus ln of 5, and there we have a local minimum. In this case, it turns out to be the absolute minimum as well on the entire set of real numbers. Okay. This is a very special case for finding the absolute maximum or the absolute minimum value of a function on an open interval. So the interval, the specified domain has to be an open interval. So let's say I have a continuous function on an open interval I, where f has exactly one critical number. So f has exactly one critical number c in I. So either at c, f is concave up or concave down. If f is concave up at c, then f has the absolute at c, f the absolute minimum. F of c is the absolute minimum. If at c f is concave down, then f of c is the absolute maximum. Now, so here's exactly what it says. So suppose that at c, f prime of c is 0, but the f double prime of c is positive. So here, this condition tells f prime of c equal to 0 tells me that I have a critical point at c where the tangent line is horizontal, and f prime of c is positive, telling me that the function is concave up at c. So therefore, it has a local minimum at c. But since we have only one critical point, it's gotta be the absolute minimum value. F of c must be the absolute minimum value of f in the interval I. Similarly, if f prime of c is 0, but if f double prime of c is negative, then f of c is the absolute maximum of f in the interval I. So let's think about it for a second, right? So what we are saying that if we have exactly one critical point where the derivative is 0, and if f has a local minimum there, that has to be the absolute minimum. If f has a local maximum at c, then that's gotta be the absolute maximum of f. Again, because we have only one critical point at c. Now, why is that the case? Well, let's look at the first case, right? So if let's say f prime of c is 0 and f double prime of c is positive, then we know that f has a local minimum at c. But why does it have to be the absolute minimum on the open interval I? Well, if that's not the absolute minimum, then that would mean that f has notice that the function is concave up at c. So if the absolute minimum occurs at another point, well, then at that point we will have a local minimum as well, which would mean that we have another critical point, but that's not the case. We have exactly one critical point. So similarly, let's look at the second case. Suppose that f prime of c is 0 and f double prime of c is negative. So that means that f is concave down and f has a local max at c. And we are claiming that f of c is actually the absolute maximum. Why? Because if the absolute maximum occurs at another point in the open interval I, then f must have a local maximum there, because this is an open interval. And if f has a local maximum there, f has a critical point there, but we are assuming there is only one critical point. So basically, in an open interval, if f has exactly one critical point where the derivative is 0, then at that point, either f has the absolute maximum or f has the absolute minimum. And if it has the absolute minimum, if f double prime of, if the second derivative is positive there, it has the absolute minimum there. If f double prime is negative there. All right, so let me explain that further in the following example. Let's say that I have the function f of x, which is 10 minus x minus 16 over x, and we are taking the domain to be the open interval from 0 to infinity. So that's I. If I look at the first derivative, that's going to be negative 1, and the derivative of 16 over x would be, so the derivative of negative 16 over x would be positive 16 over x squared. Now here we can combine the two fractions here, and we get negative x squared plus 16 over x squared, which is equal to 16 minus x squared over x squared. 16 minus x squared can be factored out into 4 plus x times 4 minus x. So the derivative would be 0 exactly when the numerator is 0, and the numerator is 0 exactly when x is either 4 or negative 4. So we got two critical points, negative 4 and positive 4. However, negative 4 does not belong to the specified domain, so we throw out the negative 4. So therefore, in the specified open interval, f has exactly one critical point. And therefore, let's look at the second derivative. The second derivative of this function, so the first derivative is negative 1 plus 16 over x squared. If we take the derivative again, we will end up with negative 32 over x cubed. Again, you can apply the power rule, or you can apply the quotient rule. So 16 over x squared, that's the same as 16 over x squared is the same as 16 over x squared is the same as 16x to the negative 2. And when you take the derivative, you get negative 16 times negative 2 times x to the negative 3. So you end up with 32 over x cubed. So that's the second derivative. And so if I evaluate the second derivative at 4, then I get negative 32 over 4 cubed, which is negative. So that means that at the only critical point 4, f has a local maximum, but since we have only one critical point, f of 4 would be the absolute maximum. So since f has only one extreme value on this interval, f of 4 equal to 2, so f of 4 would be 10 minus 4 minus 16 over 2, which is 10 minus 4 minus 16 over 4, which would be 2. This is the absolute max of f on this interval, and you can see that's the case. From 0 to infinity, this is the graph of f, and right at 4 we have the absolute maximum. So the idea is that in this open interval there is only one critical point, and at that critical point we have a local max, but then we have to have the absolute max there as well, because if we didn't, then we would be having another critical point. Okay, so this is it on the optimization of finding the maximum and minimum values of a function. In the next section, we will be applying these ideas in some application problems.